let's start. So today I want to start a new chapter. So quantum mechanics and functional analysis. And maybe I start by a very short motivation of the topic. And the motivation is needed because technically this is a complicated and cumbersome topic, so we need to know why we are doing it. So let me recall that if the dimension of the Hilbert space is finite, so then for self-adjoint operators, we are mainly using two facts. So the first one is the spectral theorem. And the second one is the fact that you can exponentiate a self-adjoint operator times imaginary units, so an anti-self-adjoint operator, and the resulting operator is unitary. So this of course is an elementary linear algebra for finite dimensional Hilbert space. Now the question is, what about the infinite dimensional case? And in principle, most of this chapter is motivated by this consideration. So there will be one more consideration that perhaps many of you know about, but we'll see it today very soon. So there will be one more extra point added to this question. But in general, all the suffering which is to come, to some extent it addresses this thing, how to get these two statements. All right, so as I said, the motivation will be short. Now let me recall or introduce some of the facts about the infinite dimensional situation. So now let's say, from now on, the dimension of H is infinite. So we still have a Hermitian bilinear form as before. So the product with itself for a vector is a square of a norm. Now it becomes, various topological notions become important. So we assume that H is complete under this norm. So in other words, recalling from the first year calculus, so Cauchy sequences converge in this space. And one more extra assumption that one usually makes, we assume that H is what is called separable. So this, the definition is that it contains a countable dense subset. So that is, there is a sequence which is dense, but in practice what is important is the following. So H admits what is called countable Hilbert basis. So a basis is a sequence such that the following properties are verified. So it's an orthonormal sequence. So the vectors are orthogonal to each other. The length of each of them is equal to 1. And then for all vectors in H, one has the corresponding decomposition according to this basis convergent to U. Or maybe let me just to recall you right in a bit more detail. So this would mean that the finite sums converge to U when n goes to infinity, and the convergence is always under this norm. And this all implies that the sequence of squares of absolute values of the projections converges to the norm of U. So right. So here perhaps a small piece of notation. So one often denotes those components or projections by UI. Now let me recall what are the examples of such separable Hilbert spaces. Maybe the main example is a space small L2. I'm not sure whether you usually put 2 as a superscript or as a subscript. I don't know what's your preferred notation. So this is a vector space formed by infinite sequences. AIs are complex numbers, and so the sum of squares converges. Right, so that's one such space. So the Hermitian product is given by the standard formula. So that's the example number 1. Now, such a Hilbert basis would be, for instance, given by the standard basis where you have 1 in the ith place and zeros in all other places. So that would be one possibility. Now, as a second point, I would like to introduce a whole class of examples. These are spaces, the functional spaces, capital L2. And here for x, let me list some of the possibilities that we'll be using soon. Say segments, for instance, segment 0, 1. A circle, the real line, Rn, and so on. So L2s form various spaces. Now let me recall what is in this case the the Hermitian product. So this is just a product of f bar times g, and here dx is typically the Lebesgue measure, but this is negotiable, right? As probably many of you know, here you can negotiate, you can introduce various weighted Lebesgue measures or do other things. Now, maybe a test question, especially for those of you who learned quantum mechanics on the physics side before. Now, I'm saying that this is an example of a separable Hilbert space. Now, how to build those bases? Why does it have such a Hilbert basis? So how do you? Of course, we'll see examples and we'll see general facts, but just like that. So what are the bases? Like, for instance, you take x equal to r.
Sine or cosine?
Ooh, really? No. Why not? So you take x equal to r, you take the sine. How normalized is going to be? Right? Not really. Yeah, right. Something. Yeah, you need to. Yeah, some complicated functions. Kind of maybe short answer, but yes, some Gaussian times whatever orthogonal polynomials. Yes, that. Right, times the Gaussian. So yes, right. So basically, you need to work to construct those bases. That's why I don't write them here or whatever. Right. So we'll see, of course, those examples. Now, maybe one small remark. You see, since separable Hilbert spaces, they all have those countable bases. In fact, they are all isomorphic to each other. So basically, the only example, I mean, if you really want, so that's the only example that you can ever consider. So if H is separable, H as a Hilbert space is isomorphic to the small L2, because you just choose your basis. Of course, it might be very difficult to construct a basis. But suppose you succeeded to construct a basis, then you simply map your basis to this stupid basis of L2, and you got your isomorphism. In practice, it doesn't always serve us very well. So this theorem is not as useful as it looks. However, one should have in mind that basically all the Hilbert spaces that we're going to deal in the rest of the course, they are all isomorphic to this small L2 with this Hermitian product. Maybe one more small remark. About those infinite dimensional Hilbert spaces. And this remark will be important for us. In a finite dimensional Hilbert space, we have typically many finite dimensional subspaces, right? But if you have a proper subspace, it always have a positive codimension. Say, in the Hilbert space of dimension 3, you can have proper subspaces of dimension 2, 1, and 0. Now, in the infinite dimensional situation, maybe let me state it in this vague way. So there are many dense subspaces. So it is possible to construct, and many, so there are many subspaces which are actually dense, which means that you can approximate any vector of H by the elements of the subspace. Let me give one very simple example, and we'll see many more examples later. So one example will be like this. So let me consider V inside small L2. Which is formed by finite sequences. So this n is not fixed. So I take some finite sequence and simply I want zeros after some point. So this is clearly a subset of the small L2. It's also a vector subspace. Because if you take two finite sequences, you take their linear combination, you get again a finite sequence, right? Now, it is also obvious that if you take A, or maybe not obvious. So if you take A, an infinite sequence now, then you see I wrote this formula, right? So the sequence of partial sums of this infinite decomposition, it converges to the vector. So then we know that an, well, sorry, maybe I should put it like this. So if I cut it at the point at the entry number n and continue with 0, so this sequence will converge when n goes to infinity to A. So this is a subspace. We see that it is dense. All the vectors are approximated by it. And this subspace, in some way, let's say, of course, we will now need to develop a filling. So this subspace is much smaller than L2, right? Because it only has finite sequences, so this guy has lots of infinite sequences. Okay. Maybe one more example so I said I will not be giving you the Hilbert basis, but maybe in one case I still want to write a Hilbert basis. So let's consider another example. So H is L2 of a circle. So we have a circle S1. And for a circle, let me choose this model. So I consider this segment 0 to pi, and I identify the endpoints. Now, what's the Hilbert basis here? I guess now your previous answer would work very well. So what will be an example of a Hilbert basis? So what kind of functions we would usually choose as a basis in L2 of a circle? Right? So those exponents, and if you want to normalize them, I think we should probably put 1 over square root of 2 pi. So that's a Hilbert basis. And now those components, so if we consider the scalar product of En with some function u, so this will be an elementary Fourier transform on the circle. Right. So in this case, so this statement is u of x is equal to the sum over n's in z, and here will be this un exponential I n x 1 over square root of 2 pi. As experts in quantum mechanics and in analysis, so this formula, what's the meaning of this formula? How does this convergence work? In which way does it converge? Yeah, that's right. So in principle, it's not like if you choose u to be some very good function, maybe it also converges pointwise. But this is in some way less guaranteed, right? What is for sure guaranteed by these general statements is the convergence in the Hilbert space. So it converges in the norm of L2. So one more thing that I would like to recall. So suppose you have a linear operator between two Hilbert spaces. So, so this operator is called bounded. If there is a positive constant such that the norm in the second space of the image is bounded by this constant times the norm of the norm of the vector in the first space. Now we'll mainly be interested in maybe then one more thing. The operator norm is introduced is a supremum of those ratios. Of course, if it's bounded, then the supremum is finite. And of course, an operator is called unbounded if such a bound does not exist. So we'll be mainly interested in two situations when those two h's are the same. And the other situation, which is really simple, when H2 is simply a one-dimensional vector space, right? So in this case, we consider linear functions or linear functionals on H, and there is the following fundamental theorem of Ries, which says the following. Every bounded linear functional on H is of the form so let me write it in the following way. So I denote it by LU, and I will now say what U is. And this is simply a Hermitian product with a vector in H. So the only bounded linear functionals, they are scalar products with vectors of H. Maybe, as usual, I just want to know, so who learned Riesz theorem in your previous life? Okay. So this is maybe, for those who never seen it before, maybe it's a good idea to just look at it. So this is a fundamental property that we're going to use often. Maybe also a small exercise. Show that this linear functional is actually bounded. And to use is the Cauchy-Schwarz inequality. Right. Okay, so much of the boring introduction. Now I don't know whether the rest will be less boring, but for sure it's more sophisticated. So now we start thinking about operators. On H. And here the point is, so the mathematically natural class of operators that one should study are bounded operators. However, it doesn't go well together with the purposes of quantum mechanics, because quantum mechanics typically wants to work with unbounded operators. So in a way, for this reason, in mathematics, the whole theory of unbounded operators was developed, and I will now show you parts of that theory. So we will be looking at possibly unbounded operators. So such an operator will be a map from a subspace of H, which is called the domain. So from the domain of H to H. We'll be making various assumptions about this domain, but one natural assumption is as follows. That this is a dense subspace. So recall, we have lots of dense subspaces, so we assume that D of A is dense. Now here is the definition of the adjoint operator, right? Recall that before we had some kind of simple definition. Now one has to think a little bit of what it is. And first of all, one should think where this adjoint operator will be defined. So the adjoint operator is defined on the following domain. So these are vectors V of H, such that the map from U to VAU, the product, is bounded on D of A. right? So this map is well defined on D of A because AU is a well-defined vector. Now we can take its Hermitian product with V. So this is clearly linear in U. So it defines a linear functional. Now we require it to be bounded. So it's all kind of in some way consistent. So now assuming V is in this domain, then by Riesz theorem, there is a vector V star in H such that this guy is a scalar product or a Hermitian product with V star, right? Now, in principle, it may happen that there are many of such V stars. Who knows? But actually, V star is unique since the domain is dense, right? So we know all the Hermitian products with elements of a dense subset. It's bounded. Now we can uniquely extend it to the whole of H, and then V star is clearly unique. Okay, and then finally, we define A star on the vector V, right? V belongs to the domain of A star, and we define A star on that vector as V star. Now, here there is a consequence, right? Before this was our main definition. So the consequence is that VAU is equal to A star VU, right? So here I just replace V star with A star V. And this is now true for all A in the domain of U and V in the domain of A star, right? So before this was the definition of A star in a finite dimensional setting. Now maybe a small remark. D of A star is not necessarily dense. So in principle, that's something to worry a little bit about. So in principle, we would like to have operators with dense domains. Now the domain of A star may be not necessarily dense. So later on we'll see various examples, and especially in the next problem set you have various examples. Now I would like to give a couple of more definitions and maybe one property. So proposition the kernel of A star is equal to the orthogonal of the image of A. So this is essentially the same as so this fact is basically defined dimension as in the finite dimensions. And the orthogonal of A, these are all the vectors which have a zero Hermitian product. Sorry. With all the vectors in the image of A. Right. So proof. So we'll be using, of course, this equality. So if V is in the kernel of A star, then the right-hand side on this formula is 0. So this means D of A, right? And that of course means that V is orthogonal to the image of A. So that's basically this formula which tells us. Now the other way around, let's say V in the image of A orthogonal. So then what? Then we see that A star V U is equal to 0 for all U in D of A. And now since D of A is dense, this means that this guy is 0, right? So the only thing which vanishes on all the vectors is 0. So by the way, another test question. So how do you actually show that? I'm now saying, right, since D of A is dense, now this implies that this guy is 0. So actually, and what's the formal proof? What should one do? Yeah, it sounds convincing.
Take U, which is almost A star V, which is near A star V.
Yeah.
And
Okay, that sounds correct, but not sufficiently precise, right? Since D of A is dense, I can make a sequence, right, which converges to A star V. So then this thing, which is 0, this sequence of products will be convergent to the norm of A star V, right? And so we conclude that the norm of A star V is 0. And then A star V is 0. Right? That's a formal proof. Okay. All right, so that's an important property. Now, one more definition, or maybe a couple of more definitions. So we say that A, what's the notation that I want to use here? That A is contained in B if the domain of A is a subspace of the domain of B, and A and B coincide on all vectors of the domain of A. So and also maybe we can say we say that B is an extension of A. And maybe one more definition. A is symmetric if AUV is equal to VAU for all U and V in D of A. So note that before, this was actually the definition that we wanted of A being self-adjoint, right? In finite dimensions, that's the definition of being self-adjoint. Now, it turns out that's in some way wrong or insufficient definition. So it's not enough to have this property to have all what we want, like the spectral theorem or exponentials being unitary. So this is, maybe that's an important thing. That's really not enough. So we'll have to work more. But now, okay, still, that's a very useful and very important definition. And maybe we'll see whether it fits here. One small remark. So let's compare this formula to the formula on the other blackboard, right? So here we know that for V in the domain of A star, we have this formula, and here we have A star. Now, what do these two formulas, how do these two formulas talk to each other? Right? So by definition, V is in the domain of A star if this thing is a bounded linear functional on U. Now, by this formula, so this right-hand side is equal to this, right? Sorry, I wrote here in the wrong way. So in fact, we see that in this setup, this is definitely a bounded linear function of U defined by this guy, AV, right? So the remark says that for A symmetric, so the domain of U of A is contained in the domain of A star. And in fact, A star is an extension of A, right? Because again, by the same formula, they actually coincide, A and A star, on the elements of the domain of A. In particular, another interesting thing, right here you see we were a bit worried that the domain of A star may be not necessarily dense. But now, if A is symmetric, so then the domain of A star contains the dense domain of A, and so it is dense. Perhaps it would be good to finish this hour with a definition of self-adjoint operators, but we still have some work to do. So let's have a break and let's finish the definitions after the break. All right, so let's continue. So unfortunately, I have to continue a little bit more with the definitions before giving you the main definition of today, the definition of self-adjoint operators. So, definition. The operator A is called closed. If it's graph, so the graph is a set of pairs of vectors, right? U and its image. So this is sitting in H times H. And of course, we consider U in D of A. So if this graph, and this is a subset in H tensor H, right? Each of the H's has a norm, so it's a topological space. And this graph may or may not be closed. So we call an operator closed if the graph is closed. Maybe just to say, in other words, what this means. So this means the following. Suppose you have a sequence of vectors in the domain of A which converges to some vector a priori in H. And let's assume that the images also converge to some other vector. So then if the graph is closed, so then, in fact, U will be in the domain of A, and V will be the image of U. But this does not need to be the case, so this is not guaranteed. So in the exercises, you will have an example of a situation when that's not the case. So this is not something which is guaranteed. So maybe a small proposition. In fact, the operator A star is always closed. So why is it true? Well, suppose we have a sequence of vectors in the domain of A star which converge to some vector V, and the images converge to some vector W. So then let's do the following. Let's choose now some vector in the domain of A, and let's consider this Hermitian product. So I take AU and I pair it with V. Well, now this is a limit n to infinity of AUVN. Maybe, do you mind if I maybe just let me change, let me conjugate. Right. Okay. Now, of course, right now U is in the domain of A and Vn is in the domain of A star, so I can use under the limit the property of A star, right? So I can pass it on the other side. But now these guys, they also converge, right? And they converge to W, so this is equal to WU. But now recall, if you still recall, the definition of the domain of A star, right? So the domain of A star, these are such vectors V, so as this expression is a bounded linear function on U. But this is certainly a bounded linear function on U, right? So this is of course bounded linear on U. So therefore, V is in the domain of A star. And then by definition, right, this guy, W, is equal to A star V. And that's exactly the definition of being closed. So for A star, this fact of being closed is not a problem. Now, the next definition. A is closable if it admits closed extensions. So in fact, it turns out that if A is closable, then there is a minimal closed extension. That we denote by A bar. And for this closed extension, the graph of the extension is simply the closure of the graph of A. Maybe informally, so you will see in the exercises in which way the operators can not necessarily be closable, and roughly speaking, how this may happen. Of course, once you have the graph of A, you can always consider its closure, right? So what may be the problem? Why is it not a graph of A bar? It is not, the problem is that this closure is maybe not necessarily a graph of anything, right? So, and you will see an example of it in the exercises. But if it is a graph of something, this something is an operator which extends A. And this operator is the minimal closure, which is A bar. Okay. So now the remark. We see that so assume A is symmetric. And closable. So then, so there is this minimal extension. And of course, it is then contained in A star, which is just some extension, right? A star is an extension. So the minimal extension contains A, and some extension, which is in this case A star, contains A bar. Now, the key definition. A is self-adjoint if A star is equal to A, as before. But of course, here the key feature, so of course A has to be symmetric, right? or maybe let me put it this way. The symmetric operator A is self-adjoint if in addition A star is equal to A, which means that the domain of A star is the same as the domain of A. And it is called essentially self-adjoint if A bar is equal to A star. So we'll see that this is, at first sight, it sounds a little bit of strange notion, but it turns out that it is technically very useful. So this means that you see maybe you didn't choose the domain of A well from the very beginning, but then you take a graph, you take a closure of the graph, and that's the graph of A star. Right? So that's also a very good situation. So that's the main definition of today. And sorry for torturing you with this kind of tower of definitions which go one on top of the other. Maybe it's a good time to look at some examples. So there will be more examples in the exercises, but let's do at least some examples already now. So the first example will be like this. So I choose H to be the small L2. And I choose a sequence of complex numbers. So inside L2, I choose a subspace which will be the domain of A. And let me just choose this space of finite length sequences. So sequences which become zero after some point. Now I define my operator A on the standard basis. And I simply define it in this way. So all the elements of the standard basis are eigenvectors of A. Now maybe the first question is whether A is bounded, right? Now it's clear that if the sequence is bounded, then A is bounded. So that's just for the following reason, right? So suppose I want to compute the norm square of the image of some vector, right? So this is equal to norm squared of ui aei. Now I always have finite sums. Now since aei is just small aei, right? So this is equal to sum from 1 to n ai squared ui squared. And this is bounded by c squared of ui squared. And this is c squared times the square of the norm. So this shows that if the sequence is bounded, then A is bounded. So what about if the sequence is not bounded, right? So then recall, right, we had the definition of the norm. As a supremum. Now, well, I I even don't need all the u's, right? I only take the basis vectors. I already get infinity as a supremum. So the operator is unbounded. Right, so the operator is bounded or unbounded depending on the properties of this. Oh, sorry. That was not very clever, right? How should I denote them? U, right? Is it better? Because otherwise, right, that was the same notation as the sequence. So that's not very good. Sorry. Okay. Now what about A being symmetric? So I claim that A is symmetric if and only if what? Yeah, so they're all real, and let me show it. Let me show it in one direction, and you show it in the other direction. So let's say if A is symmetric, this means that A EI is equal to EI A EI, and this is AI EI EI, and this is equal to AI, and this is equal to AI bar EI EI, and this is equal to AI bar, right? So you show it in the other direction. Well, now, finally, a somewhat interesting question. Is it actually self-adjoint? In fact, you will answer, or whatever, you will study it in more detail in one of the exercises. But so let's determine the domain of A star, right? So the question is, what's the domain of A star? Okay. So let's recall the definition. So these are elements V in H, such that VAU is bounded, right? Is bounded as a functional of U. Okay, what is VAU? So this is equal to sum or I from 1 to n. Let's recall that here it ends at n. We can actually write till infinity. That may be even better. So vi bar times ai times ui, right? So, so the question is when this thing is bounded. Now, we know that if it is bounded, it is a scalar product with some vector, right? So it has this form. And this is for all u which are in D of A. Well, but u in D of A, this is any u of finite length, right? So this means that in fact, this equality for some finite length u, it will imply the equality of the coefficients for any finite length. This means for all I, right? So this means actually Wi is equal to Ai Vi. And so this should be bounded. This should be bounded linear functional, which means that W has to be a vector in L2. So this means that the sum now from 1 to infinity, ai square vi square has to be finite. So we conclude what's the domain of A star. So these are vectors in L2. Sorry. Such that the weighted sum of weighted infinite series converges. Now, one of the exercises, and maybe actually it's even a homework, is to show that actually this operator A star is self-adjoint. And then A is essentially self-adjoint. So that's the correct, you see what happens, maybe just a little bit of a feeling in this simple example. So we started with a domain of definition, which was kind of very small. So it's too small for the thing to be self-adjoint. Now what happens, we find a good extension of this domain, and that turns out to be the correct domain. That's where we should have defined it from the very beginning. But of course, like in the beginning, we didn't know, and that's how we discovered that domain. Maybe now one example where we are starting to touch base with more realistic quantum mechanics. As I said, we can in principle work with L2 all the time, but quantum mechanics comes from physics, and there small L2 is not the most natural Hilbert space you want to work with. So the next example will be H equal to L2 of the segment 0, 1. So we'll choose the domain of our operator. You see, I have to do it in a bit strange way. I first say what is the domain, and then I say what is the operator. So this will be the space of smoothly differentiable, continuously differentiable functions on 0, 1 with values in complex numbers, and which is equal to 0 at the boundaries of the interval. So this 0 corresponds to boundary conditions. Now the operator A will be minus I the derivative. In quantum mechanics, it's usually referred to as the momentum operator. To be quite precise, one puts here h bar, but we're not going to put here h bar, just forget about it for a moment. Okay, so when you take this continuously differentiable function, you differentiate it, you multiply by minus I, you get a function which is continuous. So this means it is an L2. So it's a well-defined operator. Now let's discuss its properties. So first of all, an easy exercise. A is a symmetric operator. Well, what does one need to check? So I need to compute U AV. So this will be an integral from 0 to 1. U bar of x, and here minus I dv over dx. Well, one can integrate by parts. So, right, everything is continuously differentiable to get minus u bar of x v of x from 0 to 1. Now, plus I integral from 0 to 1 du bar over dx v of x dx. So since u and v, they vanish at 0 and 1, this is actually equal to 0. And this thing I can rewrite as integral 0 to 1 minus I du over dx bar v of x dx. And this is equal to a uv. Right? So this kind of standard calculation works very well. So this operator is definitely symmetric. Now, what about being self-adjoint, or at least essentially self-adjoint? So I will not do the full analysis of this question. However, I'll give enough remarks to show that it is not essentially self-adjoint. So it's not self-adjoint, there's no question about it, but it's even not essentially self-adjoint. So claim it is not essentially self-adjoint. Okay. So why is it true? First of all, let's say I claim that continuously differentiable functions now without any boundary conditions. So they're all in the domain of A star. Why is that? Well, suppose I take such a function. We were denoting it by v, right? So then you see. So in the equality, and let me also claim that a star v is given exactly by the same formula, right? So that's the claim. So why is it true? Well, essentially, the thing is, when we derived this equality, here it was enough that one of the functions vanishes at the endpoint, right? You don't need both functions to vanish. So let's say one of them doesn't vanish and the other does. So then still the equality between the two integrals, the integration by parts, is okay, right? So then this means I see that v au is equal to a star v u, and this element is of course in H, right? So we actually see that this integral identity implies this formula, right? So the expression VAU is representable in the form of the scalar product of some vector with our u. This means it is a continuous functional, and this means that v is in the domain of a star, and a star of v is its image, right? So basically just the same formula shows that this is true. So so v is in D of a star, and a star acts by this formula. Okay. So what? Now let's think. So I want to prove that a bar is not equal to a star. So I will be thinking about the closure of the graph of A. Now, what's the closure of the graph of A? So a point in the closure of the graph of A, so it's a pair, such that there is a sequence of elements in D of A which converges to U, and the images converge to V, right? And of course, convergence is always NL2 of 0, 1. So, so I claim that with this procedure, I will never get those functions which are non-vanishing, with non-vanishing values at 0 and 1, right? So here I'm getting arbitrary, of course, continuously differentiable functions v with arbitrary values at 0, 1. And here I will show that actually this is not true. I cannot get those functions. All right. So so let me start with this sequence un, and I will write the following trivial formula. So un of x is equal to I integral from 0 to x minus I du over. Do you mind if I, right? That's certainly not a very good notation, but do you mind if I don't change the name of the variable? Right? After all, we're not in the first year. We all know what I have in mind. Is it okay? Right. So, of course, right, this is true. This is because un of 0 is 0, right? All un's, they have a value 0 at 0, so I can represent them in this way. I want to rewrite it as I integral from 0 to 1, and there I write a characteristic function of the segment 0x, so it's equal to 1 on that segment and 0 outside, times minus I du over dx. Is it okay? Right. Now actually, right, that characteristic function is equal to 0 or 1. Do you mind if I also say it's complex conjugate? It's a real function, so it coincides with its complex conjugate. Now this is equal to I of the Hermitian product in L2. Sorry, this was un, right? With a un. Now we know that a un converges to some, in L2, to some function v, right? So this converges when n goes to infinity to I to I 0x v. Okay. So let me denote this function by u tilde of x, right? So this is a function of x, because I just consider those L2 Hermitian products and I obtain some function of x. So, so there is this convergence, and I note that note that this convergence is uniform in X. So that's relatively easy to show. You use again the Cauchy-Schwarz inequality, right? AUN converges to V, so the norm of this difference falls to 0, and the norm of these guys is bounded by 1. Right? So therefore you can write a bound which is independent on x for this convergence. So this means the convergence is uniform in x, and since the convergence is uniform in x, you know that this guy was equal to 0 at 0 and 1, then its uniform limit is also equal to, it's going to be also a continuous function. So then this is in C of 0, 1, and u tilde of 0 is equal to u tilde of 1 is equal to 0. Okay. Now, so what? Now we have two things. So this sequence un converges to u in L2, and it also converges pointwise uniformly to u tilde. So what can one say about u and u tilde? Now maybe I write it here again. So un converges to u. Well, of course, this means that the sequence can only converge to one limit, and the convergence, uniform convergence in C implies convergence in L2. So this means that as L2 functions, U and U tilde are the same. Maybe I should recall, I don't quite know how, right, the elements of L2, they are defined modular changes on measure 0. So in principle, they may be different on the set of measure 0, but it basically doesn't matter. So if my words don't make much sense for you, don't worry. So these two things are the same. So this means that if U in the domain of A bar, right, then U of 0 is equal to U of 1 is equal to 0. And this means that D of A bar is not equal to domain of A star. So that's because, right, in A star we saw there are functions with arbitrary values at the boundary points, and this proves our claim. So A is not essentially self-adjoint. Now, you know, maybe I should say that today I've shown you the examples that I thought would be a little bit interesting that something doesn't work. Of course, in principle, in quantum mechanics, we want things to work. So here I showed you things which don't quite work. So on the one hand, in the exercises, you will see things that work. And on the other hand, so now specialists in quantum mechanics, what do you say about this problem? What should one do? All right, so this operator, this is a momentum operator of some whatever particle. So this operator is not self-adjoint, it's even not essentially self-adjoint. So it's a kind of trouble. So now quantum mechanics experts, what should one do? What's the next step? So how is it particles don't move on segments or what? What happens?
Add more boundary conditions.
Add more boundary conditions.
Oh, I mean less actually.
Less. Yeah, sure. One needs to do something, right? So these are two restrictive boundary conditions. So one example, one way out that you will see in the exercises is to go from those boundary conditions to boundary conditions where U of 0 is equal to U of 1, but is not necessarily equal to 0. So this is called periodic boundary conditions. Topologically, this means that we replace a segment by a circle. So then kind of one of the tasks is to show that the corresponding momentum operator is now self-adjoint. So nothing like this happens. But we'll see more of examples, more of interesting examples next week. And just to remind you that next week, I think we meet twice, right? So this will be the first week when we meet twice. Okay, well, that's